Hello friends, welcome back to my channel Engineering Mathematics djganit. In this lecture series, we are going to discuss methods for solving higher order partial differential equations. We have divided the methods of solving partial differential equations into two categories. We have seen one lecture series on the methods of solving first order partial differential equations, and in this lecture series our focus will be on partial differential equations of order greater than 1 that we will consider as higher order partial differential equations. Why we are discussing these two types separately? Because the methods of solving first order partial differential equations and higher order partial differential equations are different. Therefore, we are discussing these two categories separately. And if you have not seen my lecture series on first order partial differential equations, you can watch it on my channel djganit. And from this lecture onward, we are going to focus on the methods of solving higher order partial differential equations. In first order partial differential equations, we have seen linear as well as non-linear partial differential equations. We have discussed the methods for solving linear first order PDE as well as non-linear first order PDEs. But for higher order PDEs, we are going to discuss only linear partial differential equations, because non-linear partial differential equations of higher order are not easy to solve. We are not having analytical methods for solving non-linear PDEs of order greater than 1. So for higher order partial differential equations, our focus will be linear partial differential equations. And we recall the definition of linear differential equation. It is same for ordinary as well as partial differential equation. Suppose we have dependent variable as z in our partial differential equation, and suppose independent variables are x and y, then any partial differential equation with z as dependent variable and x and y as independent variable is called linear if the dependent variable, that is z, and its derivatives, its partial derivatives, because we are having two variables. So if z and its partial derivatives appear in first degree only, the power of z and any of its partial derivative is 1, and they are not multiplied together. And that we can generalize for function of n variables also. So a partial differential equation is called linear if it is of the first degree in the unknown function z and its partial derivatives. So remember this definition, and our focus in higher order partial differential equations will be on linear differential equations only. For example, if I am writing this equation, third order derivative of z with respect to x minus 2 times third order derivative of z with respect to x 1 time and with respect to y 2 times plus 2 times say del square z by del x square equal to say e raised to 2x plus 3y. Then this is linear partial differential equation. We can see that power of each derivative is 1, or degree of each derivative of z which is present here is 1, and there is no product of z and its partial derivative. Dependent variable is not multiplied with its partial derivative. So that is the meaning of linear partial differential equation. And here we can see that these coefficients are constant. Here coefficient of this derivative is 1, here it is minus 2, here it is 2. So this type of partial differential equation in which coefficients of all the derivatives of z are constant is called linear partial differential equation with constant coefficients. As in the case of ordinary differential equations with constant coefficients, Here also our focus is on linear partial differential equations with constant coefficients. If all the coefficients of z and its derivatives are constant, then partial differential equation is called linear partial differential equation with constant coefficients. Suppose I am having del square z by del x square plus xy into del square z by del y square equal to 0, then this is not linear partial differential equation with constant coefficient, because here this is function of x. Coefficient of second order derivative of z with respect to y is function of x, or it is not constant. So this is not linear partial differential equation with constant coefficient. This is linear partial differential equation with constant coefficient. And we are going to understand certain notations also. As in the case of ordinary differential equations, we will denote partial derivative of z with respect to x by capital D. Similarly, partial derivative of z with respect to y will be denoted by d dash. So remember these notations. Capital D stands for partial derivative with respect to x. Capital D dash stands for partial derivative with respect to x. So suppose I am interested in writing del z by del x, then I will simply write dz, and similarly del z by del y can be written as d dash z. Similarly, if I am interested in the notation for del square z by del x square, then this I can rewrite as del by del x of del z by del x, and del z by del x is nothing but dz. So del by del x of dz, and del by del x is denoted by d, that is d dz, that is d square z. Similarly, if I am interested in writing this in the form of d, then because I am having third derivative with respect to x, I will write d cube z here. Similarly, if I am interested in the notation for del cube z by del y square, then for derivative with respect to y, we are using d dash, del square z by del y square, that is del by del z of del z by del y, and this I can rewrite as this is del by del y. Derivative is with respect to y 2 times. This is nothing but d dash z. D dash stands for partial derivative with respect to y. Again we are using, or we are replacing del by del y by d dash. So we have d dash z, that is d dash square z. Second order derivative of z with respect to y will be denoted by d dash square z. Similarly, third order derivative of z with respect to y will be denoted by d dash to the power z to the power 3z. So remember this type of notations, we are going to use them frequently. Suppose I am interested in writing del square z by del x del y, then this I can rewrite as del by del x of del z by del y, that is del by del x del z by del y, that is d dash z. D dash stands for partial derivative with respect to y, and for partial derivative with respect to x we are using capital D. So this we will replace by d and d dash z. Del square z by del x del y will be denoted by d dash z. Same thing we can use for higher order derivatives. Suppose I am interested in the notation for del cube z by del x square del y, then there is derivative of z with respect to x 2 times, that is d square, and derivative of z with respect to y single time, that is d dash and z. Similarly, if I am having del cube z by del x del y square. Then here partial derivative with respect to x is 1 time, partial derivative with respect to y is 2 times. So this is d dash square z. So remember these notations, d and d dash for partial derivatives of z or partial derivatives of given function with respect to given variable. Now here I have written certain examples of linear partial differential equations with constant coefficients, and we try to write them in terms of these notations. Del square z by del x square, derivative of z with respect to x 2 times, that is d square z, plus 3 times derivative of z with respect to x and y both, that is d dash z, plus 2 times here derivative of z with respect to y 2 times, that is d dash square z equal to 0. And this we can rewrite by taking z common, d square plus 3d times d dash plus 2 d dash square z equal to 0. Similarly here you can see I have del square z by del x square, that is d square z minus del square z by del y square, that is d dash square z equal to x minus y, and this I can rewrite as d square minus d dash square z equal to x minus y. Same thing we can do for this. Now I am taking z common directly. Here I am having partial derivative with respect to x 3 times, that is d to the power 3 minus 2, partial derivative with respect to x 2 times, that is d square, partial derivative with respect to y single time, that is d dash. Similarly here partial derivative with respect to x single time and with respect to y 2 times, plus 2 times partial derivative of z with respect to y 3 times, that is d dash cube z equal to 0. Now we can observe that in the multiplication of z here, if you see this function, this is a function of two variables, capital D and D dash. So I can rewrite it as a function of d and d dash denoted by capital F of d dash z equal to 0. Same thing here, f of d dash z equal to x minus y, where f of d dash is d square minus d dash square equal to x minus y. Here this is our function of d and d dash z equal to 0. Try to observe all these things which I am doing here. Now if I rewrite this in terms of notations of d, then this is partial derivative with respect to x single time minus d dash square, because derivative with respect to y is 2 times, z equal to 0. And here if we find our function of d and d dash, what is that function? D minus d dash square. Similarly let's try to write this. This is d square minus d dash square plus d minus d dash z equal to 0, and here function of d and d dash is d square minus d dash square plus d minus d dash. Now try to observe all these equations. All these equations can be written in this form, that function of d dash z equal to some function of x and y, because here z is a function of x and y, and we know that all these equations are linear partial differential equations with constant coefficients. Our interest is in the linear partial differential equations with constant coefficients, and we are understanding different ways of writing these linear partial differential equations with constant coefficients, and we are trying to develop some general form. So by observing all these things, we can be sure that any linear partial differential equation with constant coefficients can be written as some function of d dash z equal to some function of x and y. So now, depending on the right hand side function, we have two types of linear partial differential equations with constant coefficients. If right hand side is 0, that is this function is 0 for all values of x and y, then this equation is called homogeneous linear partial differential equation with constant coefficients. And if fxy is non-zero, then PDE is called non-homogeneous, as in the case of ordinary differential equations. Here we have 0, so this is example of homogeneous linear partial differential equation with constant coefficients. This is also having non-zero function on the right hand side. Fxy is x minus y, so this is non-homogeneous linear partial differential equation with constant coefficients. So remember that we can always write linear partial differential equation with constant coefficients in this form, and if function on the right hand side fxy is 0 for all x and y, then this equation is called homogeneous partial differential equation. And if we have non-zero function on the right hand side, then partial differential equation is called non-homogeneous partial differential equation. So this is one characterization. We are understanding linear partial differential equations with constant coefficients, and they can always be written in this form, as I have seen with the help of examples. And depending on the function on the right hand side, if that function is 0, equation is called homogeneous. If function is not 0, then equation is called non-homogeneous. Or you can simply remember that if right hand side is 0, after writing our equation in this form, if right hand side is 0, equation is homogeneous, otherwise it is non-homogeneous partial differential equation. This is one characterization. Other characterization depends on this function of d and d dash. If you observe here if we consider degrees of d and d dash in every term, then here in this term degree of d is 1, so degree of this term is 1 and degree of this term is 2. So degree of every term is not same here, or in other words, this function is non-homogeneous in d and d dash. If degree of each term is same, then function is called homogeneous function. So here it is non-homogeneous f d d dash. If you observe here, this term has third degree, here also degree is 2 plus 1, that is 3, here also degree is 3, here also degree is 3. That is, this function f of d d dash in this equation is homogeneous. So depending on the nature of function also, we have different methods of solving linear PDEs with constant coefficients. If you observe here, then this is homogeneous function of d and d dash, and degree of each term is 2. So when this will happen, if in each term order of derivative is same, if in every term of differential equation order of derivative is same, here we can see all the derivatives appearing in the PDE are of second order, then f d d dash will be homogeneous in d and d dash. So this is f d d dash in which every term has constant degree 2, and that happens because in this equation order of all the partial derivatives is 2. Same thing here, we have two partial derivatives and both are having same order, therefore we have homogeneous function f of d dash as d square minus d dash square. And here also you can see f of d dash is homogeneous because all the derivatives appearing are of third order. This is also you can see here order of derivative is 3, here also 3, 3. So if you write f d dash, for this it is d cube minus 4d square d dash plus 4d dash square. This is going to be function of d and d dash, and you can see it is homogeneous function of degree 3. In every term degree is 3, therefore capital F is a homogeneous function of d and d dash. Here capital F is not homogeneous in d and d dash because here partial derivative is of first order, this partial derivative is of second order. So whenever we have order of every partial derivative appearing in the equation is same, then f d dash will be homogeneous function of d and d dash, otherwise it will be non-homogeneous function of d and d dash. Here also we can see that degree is not same for each term, therefore this f d dash is non-homogeneous function of d and d dash. We can write capital F for this equation also. Here f of d dash is d square minus d dash square plus d minus d dash. Here degree of this term is 2, degree of this term is 2, this term has first degree, this term has also first degree, therefore f d dash is non-homogeneous function of d and d dash. So this is important characterization because depending upon the nature of f d dash also we have different methods of solving this type of linear partial differential equations with constant coefficients. So what we have understood is that if we have linear partial differential equation with constant coefficients, then we can always write it in this form. This is the general form of linear partial differential equation with constant coefficients, where z is a function of two variables x and y. Now depending upon the nature of this function f of xy, we have two characterizations. If fxy is 0, differential equation is called homogeneous. If fxy is different from 0, differential equation is called non-homogeneous. And for this function also, function of d and d dash, we have two characterizations, that f d dash is a homogeneous function of d and d dash, and f d dash is a non-homogeneous function of d and d dash. So remember these characterizations because methods are different. When f d dash is a homogeneous function of d and d dash, methods are different when f d dash is a non-homogeneous function of d and d dash. Similarly, we have different methods for solving homogeneous partial differential equation and non-homogeneous partial differential equation. So with this we stop this session, and in upcoming lectures we will continue with methods of solving partial differential equations with constant coefficients, and we will see that in each case methods are different and we will understand those methods one by one. So this is all about this session. I hope you like it. Thanks for watching.